All right. Section 2.1, thank you, is on quadratic functions and models. So we've been looking at quadratics thus far, and we're going to look at them some more this chapter. So when you hear the word quadratic, what does that mean? What do you think of when you hear quadratic? Four, because of four things, right? So there are actually four terms in a full-on quadratic function. It is actually an f of x equals a times some x squared plus a b times x plus a c, provided that a, b, and c are real numbers and a can't be equal to 0, because we have to have something to take times that x squared to make it quadratic. A 0, we're back to a linear function. So we should think of parabolas, right? We've been graphing last chapter, learning the translations and stretches and so forth with that. So when a is bigger than 0, we know that it opens upward. When a is less than 0, it's reflected across the x-axis, so it's opening downward. And we've talked about it a little bit. We haven't formally mentioned it too much, that there's a vertex involved with quadratic functions or parabolas. And we also have an axis, or an axis of symmetry. And it just means that it's a mirror image on both sides of that axis. Okay, nothing new here. This is review from last chapter, review from last year. So the standard form of a quadratic is what we were actually working with all last chapter. We had it in a nice, neat format for you so that you could easily pick out what was A, what was H, and what was K. Okay? The vertical axis is this line where x is equal to h. It is a straight line up and down. The vertex is the point, the ordered pair h comma k. So we have to make sure that we change the sign of whatever is in here with x and pull off our k, which is hanging out at the end. Your k is that vertical shift. The h is your horizontal shift. It opens upward again if a is positive, and opens downward if a is negative. And of course, a has that ability to stretch it as well. So it's wonderful if we have it in this format because we can visually look at it and just pull those numbers off, right? We can find the vertex immediately. But what happens if we have it in the more common form that we were used to seeing back in Algebra 2? Something x squared plus something x minus something. Well, remember that we're really liking having a perfect square here, don't we? An x minus h, something of that sort. If we factored x squared plus 10x plus 25, what did that factor into? Yeah, x plus 5 and x plus 5, which can be simplified or rewritten as x plus 5 quantity squared. Okay? That could be our h in a parabola, right? A negative 5 could be our h. What do we factor x squared minus 4x plus 4 as? X minus minus and 2 and 2. So this is the perfect square trinomial x minus 2 quantity squared. Okay. This one, x minus 3 quantity squared. So it would be nice if we could write this as an x minus 3 quantity squared, because then we would know that our h is 3. Our x value of our vertex is going to be 3. To do that, we have to do a little bit of changing of our expression without actually changing it too much that we actually we actually want to change the appearance, but not actually change the actual expression itself or the function itself. So what I do is I write the -1 over here. And remember way back when in Algebra 1 and in Algebra 2 when you completed the square, you had to say, what do I do? What do I add to this to make this a perfect square trinomial? Everybody remember that? And the trick was to say, what is half of this guy squared? Notice half of 10 is 5. Half of -4 is -2. Half of -6 is -3. Half of 6 is going to be 3. But I have to add what to it? What makes this a perfect square? 9. I have to square it. So I'm going to add 3, not 3 squared, or 9, to this spot to make it a perfect square trinomial. Now, back in algebra, we would always say make sure you balance things. Add 9 to the other side as well. Okay? Isn't that the same as saying I'm also going to take away 9? Because adding 9 and taking away 9 from the same side, isn't that the same thing as adding 0? So we can change the appearance of it. Everybody okay with that? Okay. So when we do that, here's my perfect square trinomial, which is what we were after, an x minus 3 squared. And my net result of adding 9 and subtracting 9 is going to get me a -10. So if my new function is the quantity x minus 3 squared minus 10, now you can tell me by looking at it what the vertex is. What's the vertex of this parabola? 3, -10. Because it's shifted to the right 3 and down 10, and that's my beginning point. That's my vertex, the place I would start graphing. Okay, and why is it +3? Yep. So my vertex here is a +h, +k, because this guy has to have its sign changed. It does the opposite of what we think. It's right here with the x, and it's the x movement. So to move it to the other side is going to tell you how far it changed from its original position. Yes, sir. That h will always be a negative. So whenever you get, well, here it was because we were, oops, I messed up. Everybody catch my error? Yes. Should be positive, shouldn't it? I was going from here. Why should this be positive? Yep, because it is a +3. +6 is what we're trying to get here. So I apologize. Should be a -3, -10. Okay. What is this when we factor it? X squared plus 6x plus 9 is x plus 3 quantity squared, not -3. Okay. Next one. What if I asked you to find the zeros of a quadratic equation in standard form? That just means where is it going to cross the x-axis? Where is y going to be equal to 0? So don't multiply it out. Don't make any more work for yourself than you need to. I want to say 0 equals x plus 3 quantity squared minus 10. What do I do to solve that for x? Add 10. So 10 will be equal to x plus 3 squared square root. So when we square root both sides to get rid of my power of 2, x plus 3 will be equal to what? Not just the square root of 10, but plus or minus the square root of 10. Good. Teach you bad habits in geometry to only look for the positive one because we're talking distance most of the time there. But here we want to talk about all the solutions, all the possibilities. And when we take that 3 to the other side, then we'll have a negative 3 plus the square root of 10 and a negative 3 minus the square root of 10. So that's where it will cross the y-axis. Sorry, the x-axis, where y is 0. Okay. I think if I click, there's my graph. Opening up, A was positive. Vertex is shifted over to a negative 3 and a negative 10. My axis of symmetry is this line where x is equal to a negative 3. And these are my 2 points, my 2 zeros of my graph, the places where it crosses the x-axis. Okay? All right. What if A is not equal to 1? Completing the square was easy when A was equal to 1. Half of the middle term squared, added to both. But we can tell, what's our A in this particular example? Negative 2. So what's that going to do to our graph? Open down and stretch or shrink vertically. Stretch, make it a narrower, longer, grab it and pull it down. Okay? So negative 2x squared minus 4x plus 1 says we're going to leave this 1 hanging out like we did before, but let's take this negative 2 out in front so that we can do what we need to make it a perfect square trinomial inside again. I'm going to leave this plus 1 over here. So when I factor out a negative 2 from these two terms, what am I going to get? Plus 2x. Good. So now I can easily see what I would have to add in order to make this a perfect square trinomial. Half of the middle term, 1 squared. Okay, so half of 2 is 1, squared is 1. So do I just put a plus 1 over here? No, why not? Because what's my net result of what I actually did here? I didn't just add 1, I added negative 2. So in order to balance this equation, to just change the appearance without actually modifying the actual values of the equation, if I'm subtracting 2 from this side, for karma's sake, I have to add 2. Because by adding 1 in the parentheses, the net result was I'm actually taking away 2 from this side of the equation. If I add 2 to the same side of the equation, I've only truly added 0, which doesn't impact the equation itself, just its appearance. Okay? It is like dividing. I'm just holding it in place. So when I factored it, It's similar to saying I'm going to divide everybody by. And someone may have shown you a different method. If you had y equals negative 2x squared minus 4x plus 1, you could divide, first of all, take the 1 to the other side. And then divide everybody by negative 2. And this will be an x squared minus a plus 2x, right? And then we can say what's half of the middle term. 1 squared is 1. So when I add 1 over here, I would have to add 1 over here as well. And then put it back, reassemble it back so that it looks right. Okay? This is just a way of making it simpler than by factoring it out and keeping it and holding it in place. Oh, gotcha. I'm sorry. So we are adding, so yes, a negative 2 times 1 is truly adding a negative 2 for its value. Okay? So in order to balance it out, we have to add a positive 2 so that the net result is that we're only adding 0 to it and not impacting the equation itself. Just what it looks like. Okay? So we're almost there. Now we have negative 2 times our perfect square that we found by completing the square of x plus what? What's that going to factor into? Yep, x plus 1 quantity squared. And then my net result here, 1 and 2, is a total of 3. So there's an extra step of factoring out that a, and then having to remember that the net result here is not what we added, but what we added times a, so we need to do the opposite on that same side. So what's my vertex here? Negative 1, 3. What would be my axis of symmetry? Negative 1 is just a number. Axis of symmetry is a whole line. So what's a vertical line at negative 1? What's always true about that line? Y is changing, but x is staying the same, so x equals negative 1, right? Okay. Everybody remember completing the square? Just not with an a in front, probably. Okay. Your turn. Find the vertex and axis of symmetry for f of x equals 2x squared minus x plus 1. Good. So you're taking the 2 out. Okay? So when we take that 2 out, this is where it gets confusing if you're not super comfortable and confident with fractions. So f of x will be 2 times this x squared. And when we take a 2, I'm going to leave my 1 over here. When I take a 2 out of negative 1, that's like saying I'm dividing negative 1 by 2. Pretty cool with that? So that's negative 1/2. And then I have my plus 1 hanging out there. Now, I have to ask myself, what is 1/2 of the middle term squared? So 1/2 of 1/2 is 1/4, and I've got to square that guy. So 1 squared is 1, 4 squared is 16. So I'm adding 1/16 to that guy. Be careful because of this leading coefficient. I'm not actually adding 1/16 here. I'm adding 1/16 times 2, which is the same as what? 1/8. Okay, so if I've added 1/8 to the side, the net result was adding 1/8, then to balance it, to keep it the same, to keep it consistent without modifying more than just its appearance, I have to take away 1/8 as well. We're good with that? Okay, so it's always going to be half of the middle term squared. So when I took half of a half, I got a fourth, and I have to square that. Just like when we had our x squared plus 10x plus 25. This is really half of 10. 25 is half of 10 squared. Half the middle term squared. Okay? So my end result then will be 2 times a perfect square trinomial, and it will have an x minus inside, right? Because I have a negative 1/2 x, and then I'm going to have a number over here as well. So what is this perfect square? What's the square root of 1/16? 1/4. And my net result, when I take a positive 1 and I add a negative 1/8, I get a total of 1 minus 1/8 is 7/8. So my vertex (7/8) I agree with. Be careful on the negative 1/4. Positive 1/4. Yep, it's easy to forget that. And what's my axis of symmetry? Good. The line x equals 1/4. Opening up or down? Up and stretch, right? Okay. So this isn't going to be in a nice 0, 0 or 1, 1 or so forth. It's going to have fractions for its values for its vertex. How do you know it's stretched? That's this leading A over here. So the A was positive, so it's opening up. But think of it like you would with a line with slope. With slope, it made it much steeper when it was a positive 2. If it was 1/2, it would be shallower than its original line. Same thing here. This is going to take everything that we do, and when we move 1 point over, it's going to stretch it up 2 higher than what it was before. Yes, sir. You could potentially say it was a shrink horizontally, but that's typically only when we change the value of x itself to something. We multiply that value. So this should really stretch it vertically, but the net result is a horizontal shrink. Yes, sir. Absolutely. So we started out with we factored our negative 1 to get a negative 1/2. Okay, so we took the 2 out. That left me with this guy in front. And then I have to take half of that. Half of 1/2 is 1/4, and then I square it to get the 1/16. Just like over here, if I was looking at this guy, half of 10 is 5, and 5 squared gives me my perfect square. So we ended up with a 1/16 over here, but now when we rewrite this as a perfect square trinomial, it's really just the 5, so it's only going to be the 4th. Okay, so when you rewrite this as the perfect square trinomial, it's x plus the square root of whatever that c was, that guy that you put in that whatever you added to it, quantity squared, or minus depending on the case. Okay. All right. Throw this one more at you. Find the standard form of the equation of the parabola with a vertex at 1, -2, and passing through the point 3,6. Okay. So let's start with what we know. They've told us a vertex, right? Okay. Remind me, what does standard form of the equation say? Good. So we know the vertex, right? We know h and k. So our y will be equal to a times x minus 1 squared minus 2. So we've almost got it, right? The only thing we're missing is a. So what can we do to try to figure out what a is? Plug it in. Yeah, plug in points. We have our y here, 6. We have our x here, 3. And then follow our order of operations. We need to make sure that we subtract first. So 3 minus 1 is 2. And then we'll do our power. Bring the 2 to the other side. So 8 equals 4a. So what's a? So then we rewrite it as y equals 2 times the quantity x minus 1 squared minus 2. Okay. So if you know the standard form, plug your vertex in first, plug your x and y in, solve for a. Okay. How much time do we have left? 4 minutes? Okay, let me show you one more. I think there's only one problem on the assignment that's like this. We have a young child throwing a ball. Okay, when you throw a ball as a child, you think, oh, it's just going straight and then poof, it's on the ground, right? But it's actually being thrown in a parabola. Okay, the path of the ball forms a parabola. So if they give you something like this, the height y in feet of a ball thrown by a child is given as this equation, where the horizontal distance in feet is how many feet it was, thrown. Don't copy all this down, okay? Just watch, because you're gonna have one problem like it, and I don't want you to copy it all down, okay? Tell me, how do we find this maximum height? What are we looking for there? The vertex, yep. So we're looking for this vertex right here. Okay, let me show you a shortcut, because we can complete the square on this, but it wouldn't be very fun, would it? We have to factor a -1/8 out, and then take half of our middle term and square it and add it to it, and a lot of fractions dealing with it. But the nice thing is that -b over 2a is going to get you the value of x at the min or the max. Okay, if it's in not standard form, -b over 2a gets you the x coordinate gets you h. Okay, gets you the x coordinate of that vertex. Okay, so here's my a, here's my b, here's my c. If I take the -b over 2a, I can simplify that figure out what my x value is, and then plug that value in to find out what y is. And that will give me your maximum height. That's how high up this guy got. Okay? And we can look at that tomorrow, but negative b over 2a will be your friend for this. You don't want to complete the square on this one, or the one that they give you in the book. Okay? Assignment. Test is tomorrow. Okay? Section 2.1 on page 20. We're looking at 7 through 12, 15, 17, 20, 23, 30 and 31, 34 and 37, 43, 44, 47, 50, and I believe 75 is that, find that maximum height. I'm going to snap a picture of it. Feel free. If you subscribe to, if you are a Google Calendar person and you go on an actual laptop or a non-app, you can subscribe to that calendar and have it all pop into your planner or into your calendar. When we bring in laptops, we'll do that.